did the PhD in electrical engineering at the Sharif University of Technology in Iran, and then moved to High Frequency Technology Institute of Deutsche Telekom University of Applied Sciences in Leipzig, Germany, which is by now dissolved, as I heard. And until then, he focused on theoretical modeling, but then switched to High Frequency and Photonics Lab of Technical University of Berlin, where he was working also with Lars Zimmermann. Maybe some of you that joined us in Taipei, in Taiwan, remember Lars. He gave a very interesting talk. I still remember. Deniger scaling is dead, but Moore is well and alive. He taught us a lot about how people keep Moore's law alive. Okay, so finally, you went to TU Dresden, so they became faculty and is now focusing totally on integrated photonics and in particular CMOS compatible. And now he has reached, say, the quantum domain and will teach us about quantum number generation platforms. I'm very curious.
Thank you so much. A nice introduction. I would like also to thank the committee members for the invitation. This is my second time or second talk for EACN, but the previous time I could not join physically, so it was Taiwan. So today's talk is about the quantum random number generator using silicon nitride. However, this is more or less a continuation of the activity for the talk I gave 2 years ago. The idea is to exploit integrated nonlinear optics in CMOS compatible materials. And so in principle, the first step is that if one could exploit it for some application, and that was random number generation in principle. So I will give some introduction first, then I'm going to describe a little bit about the theory and simulation. I try to linger on a little bit on this topic, because I think that would be more related to the maybe experience of the audience. And then I'm going to shortly discuss about the experimental setup and demonstrations of this random number generation. So random number generation, I think there are also people in the audience who are more familiar with this topic than me, who my focus is photonic devices. In principle, there are different types of random number generation, and the way to also excite the randomness, if this is based on some quantum effect, I think people name it quantum random number generation. The community, some other, let's say, researchers believe so that if this is non-local, maybe this is quantum. But anyway, the definition we are using is that the basis is quantum. So of course, using a single photon source and beam splitter, it is possible to get this random number generation. However, with that, we need these single photon detectors, which are large, expensive, and bulky. And they need also to work at cryogenic temperatures. And but there's also some microscopic, let's say, methods to do the random number generation, which might come from the amplitude spontaneous emission or phase noise of the laser. And there are demonstrations also in Germany. There are different groups also already demonstrated this, already startups, for example, in Bremen, who work using these types of structures. So the focus here of my talk is that if you could really get this in a single photon level, and then somehow this single photon could be maybe somehow amplified, right? We are still investigating this, you know, but you will see actually what the idea here might look like. And then if this is possible to not use the single photon detector, but still maybe we can get it from the vacuum noise amplification. And this is in principle using nonlinear optics. So nonlinear optics is a topic which has been also used in quantum, but also in other types of application, computing for the sources and so on. The idea here is that when we increase the electric field in a media, in a material, for example, then the polarization of the material not only is proportional to the electric field itself, but to the higher order of the electric field, right? And with that, it is possible to actually get some interaction between the photons, right? And this is the basis, for example, if one would like to build some gate, right? Quantum gates originally have been based on these interactions. possible also to use it. I think Sebastian yesterday also told one would like to get this SPDC source, so that one photon gets annihilated, usually 2 photons get generated. And this is the way that is one of the basic sources for the, let's say, photon pair generation using this nonlinear kind of effect. Right, and mainly Chi2 nonlinearity has been used for this purpose. This is based on 3-wave mixing, right, for SPDC sources. For example, Sebastian explained yesterday, 1 photon annihilates. This is at 780 nanometer, for example, and 2 photons will be generated at 1550. But the problem is that for CMOS compatible material, actually, this Chi2 nonlinearity is almost negligible or is negligible because they have centrosymmetric structures. And therefore, there are 4-wave mixing. So this is usually the polarization is a function of the electric field to the power of 3. In principle, one needs to have 4 photons to interact with each other. And therefore, this is a little bit, let's say, weaker, but this is the only thing that is available in the centrosymmetric materials. And the idea here is that if you would like to use it, for example, for the photon pair generation, that was the talk 2 years ago, so that there are different ways to do it, right? For the Chi2 material, this has been shown already in lithium niobate, one can buy it, But 4-wave mixing Chi3 platforms also, let's say, have been explored. Recently, I had this introduction 2 years ago, but in principle, the same thing can also happen here. The focus of today's talk is in degenerate parametric amplification, or the degenerate, actually 4-wave mixing, which means that the frequency of the signal and idler are the same, right? That this is known as the degenerate case. So this could be the case for the Chi2 nonlinearity. This could be the case for Chi3 nonlinearity. And the idea here is that if you have this type of degenerate, let's say, process, what we may get is this phase-sensitive amplification. This phase-sensitive amplification could be eventually exploited to use for this random number generation or photon pair generation principle. Today, I'm going to talk about the, let's say, Chi3, or this degenerate optical parametric oscillator in silicon nitride chip using 2 pumps, right? Dual pump and blue pump. But eventually in EACN, we showed that there is an alternative way. One could use also electric field inside the silicon nitride material. The technique is known as the electric field-induced second harmonic generation. That is a topic of research. I think with Kaspar, we are now working on a proposal so that this could be also implemented. And I think this would be maybe suitable for this application of photon pair generation. Okay. The first try is that how to model this nonlinearity. So we use a resonator. So resonator is shown here. We have 2 pump input, so red pump and blue pump. And then we will have signal and idler getting generated at the output of this, let's say, ring resonator. So the first attempt is that we need to get the lasers tuned to the resonance frequency of the resonator. So we need to put the red laser here, we need to put the blue laser here, and then we will generate signal and idler somewhere, for example, in the middle. We need to consider that we have the energy conservation, so the frequency of the photons are more or less well known, and we need to design the chip in order to get the maximum phase matching so that we get a nice curve that I think Sebastian also showed yesterday. That could be used for broadband, let's say, wavelength generation. So in order to model this process, we need to see actually how these pumps are coupled with each other. So we need to write how the blue pump is evolving as it goes through the resonator, how the red pump, and then how signal and idler get generated. But other than that, we have another dynamics of the temperature of the chip as well. So we need to solve this 5 nonlinear coupled equation to make sure how the output looks like. So we solved it both in steady state, and then we find, for example, how the gain of this, let's say, DOPO process look like. Eventually, also we solved it dynamic model in the time domain. Make sure if we have a pulse, for example, in blue pump or a pulse in the red pump, how the dynamics of this random number generation or amplification of the signal and might look like. As I said, the basis of this random number generation is that we would like to amplify the vacuum noise. And then the main idea here is that we have a phase-sensitive amplification. So we looked at increasing the pump power. In principle, the gain has been plotted here. It could be up to even 20 dB gain if the pump power is really large, like 50 milliwatts, for example. One can see here the signal phase state, really the gain is higher if the signal phase is somehow at these peaks. And if the signal phase is at other dips, for example, then there would be no amplification of the light. This is a very well-known process, nonlinear optics, Chi2 nonlinearity. The idea is that if you increase the pump power to this kind of nonlinear media, if this is below the parametric amplification threshold, this leads to the squeezing of the light. This is also something that has been shown by different groups. So this is also another source of non-classical light as well. But if it gets to this, let's say, threshold of the parametric amplification, in principle, the system will be bifurcate. So in principle, one photon will be created. So there is no vacuum anymore. One photon will be created, but one photon with the probability of 1 with the probability of 0.5 with the phase of 0 comparing to the pump, or with the probability of 0.5 with the phase of pi in principle. So this bifurcation actually is something that we have also observed as well. This is really that there is nothing, and then when the pump increases above the threshold, then we will generate one photon in principle. And we believe that in higher power levels also, at least this has been something which is claimed by other researchers, and then I think we follow the same path as well. So this state gets amplified, and that is the reason for this randomness of the phase of the generated signal at this chips or this media as well. So we tried also to do this in the time domain and see how this look like in the time domain. This is more or less the experimental setup that has been explored by the different, let's say, researchers in the field as well. And we would like also to make this, let's say, bifurcation on and off using some modulators in principle. And then one can see that looking at the phase, right, there would be the buildup of the signal with a certain phase level, which is, for example, either equal to pi or 2 pi. So, and then this will be pi or 2 pi would be with the probability of 50%. And therefore, we have this random bit generation using the scheme. Investigated at different frequencies how the dynamics look like. This usually is limited by the lifetime of the photon inside the cavity. So this is really with few megahertz it is possible to generate this type of sources. In addition, we recently also studied, because the idea is that if this random bit generation can be used by telecom operators, and then I think Mark and Ming already asked us if we can provide a theoretical model for that. So the source that we used for the amplification, so we considered that this might be a vacuum noise. However, there are other noises we have not considered. For example, usually people use amplifiers, and these amplifiers usually have amplified spontaneous emission, and so on and so forth. Therefore, we studied actually how the different types of sources can be used here at the input to the resonator. If, for example, we might have Gaussian amplitude with uniform phase, or Gaussian amplitude with binary phase, or if we could use some fixed amplitude with uniform phase or fixed amplitude with binary phase. And then we try to study how the statistics at the output might look like. This might help us also to increase the speed of the, let's say, random bit generation that has been required also by Ming and Mark also to us. The result of this study will be presented, I think, in IoT conference right next month in China. Audience also there. So Menglong will present the results. So Menglong is the PhD student who worked on this topic. And eventually, I would like also to say a few words, right? This is the thing that I think will be described by Menglong in details, how the bit rates look like. Eventually, I would like also to say a little bit about the experimental demonstration that we achieved so far. So we started the characterization of the chips simply using initially with single pump. That would be something that we already shown, right? So we need to consider 4 different distinct schemes so that we have a pump in the middle, so we can create signal and idler at different frequencies, similar to the source that Sebastian showed yesterday. We would like to also make it as a pulsed pump for single, let's say, pump. So this is the pulse single pump. So these 2 have been done so far. So, but for this random number generation, if you would like to produce signal and idlers which are at the same frequency, we need to get 2 pumps actually getting circulated to the ring. This is a challenging thing that we are still struggling to get the results of this one. So, as I said, so single pump has been shown. So dual pump, it is still under investigation. Some results, right? The chips have been designed, taking into account the required dispersion and so on and so forth, have been sent for fabrication. Chips are back. Now we can measure the chips. And what we did initially to characterize the chips in the linear regime, so at low power, how the expectant ratio of these resonances are look like, how much is the quality factor of these chips? It's quite good. Quality factor around 2 millions. Then how is it possible to shift the resonator? Because that is something that we need in order to make sure that the pumps are getting circulated within the, let's say, resonator. We can shift the resonance either by increasing the, let's say, frequency or wavelength of the laser. So for that, we need a little bit more expensive lasers so that the resolution should be something at the range of femtometer, right? And then other than that, we already put some thermal phase shifter. It was similar, I think, to what Igor also mentioned yesterday. These are also silicon nitride waveguides. And by applying voltage, it is possible to shift the resonance frequency of these resonances. And that is the way that we try to also get the light circulating simply by applying voltage to chip. I don't want to go too much into details here, right? So here's the experimental setup. But the results are already, I think, there. And at least for the single pump, it is published. For dual pump, I think will be published soon. So for single pump, signal and idler generation, we try to characterize these chips. Principle, initially, we got to some comp region. And this has also a specific application for itself. These are not really soliton pumps. These are the pumps. When we increase the power, we learned how the cascaded 4-wave mixing happens so that we have multiple comps with high efficiencies. And eventually at specific, let's say, power and specific detuning, we might get this optical parametric oscillator regime in which just 2 signal and idler gets generated. So we did the full power map and so on and so forth, right? And I think the results have been published before. We learned that which frequency ranges it's possible to get achieved by this type of, let's say, sweep. For example, we could not go up to 100 megahertz, single pump pulsed OPO, but it is possible, for example, to go up to 50 megahertz. Right? This shows actually how much the speed of this random number generation might look like. Now we are continuing, also working on measuring the dual pump. So we need to make sure that both blue pump circulates. And for that, we looked at the, let's say, a transmission spectrum of the resonator. And we learned that which frequency we would like to use for red, which frequency we would like to use for blue. And then we need to also make sure that we can circulate the blue pump in the resonator and circulate the red pump circulator. This is a difficult task for now, because it is a problem we have with the thermal, right? If you would like to get the laser to the resonance frequency, the chips get warm, and therefore the resonance frequency moves away from the laser. But as soon as we set the parameters, I think then we can forget it. And this is something. So in the engineering community, this is quite a common way to do it. So we could find this, let's say, degenerate signal already with the dual pump 4-wave mixing at the continuous wave, so don't want to take it on and off. But what is still missing to be done is that when we would like to get the blue and red pump, turn it on and off, we would like to make sure that we get random number, right? So if we just use continuous wave, we have a certain phase, it remains there. We would like to turn it off and then turn it on again, there would be another phase, right? Turn it on, off. This is the next thing we are actually struggling with for the moment. I hope by the end of the year, we might have some experimental results that can be shown. This is more or less the summary of what have been discussed today, right? About introduction, a little bit about the theory I try to emphasize, and experimental setup and demonstration, right? This is still not quantum yet in the single photon level yet, but I think as soon as our receiver problem gets solved, maybe we can use high facilities so we can take the chips to Munich and measure this there. So Menglong, it's actually mainly contributed to this work. This is his PhD work. Abdou, Chandan also supported the team concerning the measurements. Also, I would like to thank the collaborators, I think in Deutsche Telekom, Ming and Mark, we are actually mainly in contact with them because they are the end users. And then also like to thank the financial support from Silhouette Project, the Quiet Project with Yanis, I think already mentioned about the ongoing project. That's all from my side.
Okay, this worked out pretty decently. Thank you very much for the talk. Can you, like one question, like the first question is a very technical one. What is your speed limit and why are you kind of like suffering like at 100 megahertz, I think? This is the first very naive question, and I have a follow-up question which is more hard.
Yes, maybe about the speed limit. I think we try to investigate it. The problem or the speed limit here is because that we would like to shoot these photons inside the resonator, you know, and when we turn the pump off, it takes some time for the photons to get, so this is known as a photon lifetime of the cavity. So we are limited by the photon life of the cavity mainly, right? And this is for this type of high quality, 2 million, this is something like megahertz or something that range, principle. We did this also in time domain simulations, and this also proves that this is limited by photon lifetime.
Okay, I see. Next question is much harder. What is quantum about it? And let's say, how do you like in principle, like I think I've wrote an own chapter on like the randomness of OPOs and like how this oscillation starts and what is the phase relation. But let's say, please, I would like to hear a kind of concise, definite argument that this is a quantum random number generator and where it originates from.
Yes, this is also something we are still investigating. And that is the reason behind all this investigation we are doing about, you know, what happens if we have different input light inside, you know. People claimed, right, this is Gaeta group in Colombia, and then Reza Marandi from Stanford University, right? They claim this is quantum. But I always get this question if this is really quantum or not, right? Because the idea here is that the basic explanation by them is that we have this vacuum state, and then when we increase the power, in principle, it gets squeezed, and then we have this bifurcation. Okay, everything is good. The problem is that it has never been, let's say, investigated in the single photon level. So this thing has never been investigated. People use milliwatts of the power inside, and this is the thing that needs to be investigated from my point of view.
What has a single photon level to do with quantumness per se? I don't get this. You claimed this like in passing. Why single photon level at all?
I don't know what you mean then. You can a little bit more explain. So
You introduced your kind of statement about random number generators, how they are designed, and you have this mimic experiment, like you send a single photon to a beam splitter, and then you say, well, there's also vacuum noise. So would you claim that the like homodining of the vacuum state is not a quantum random number generator, or I don't like this is this irritated me quite a bit.
No, the question is this. Maybe that would be a question from my side. Do you think, let's say, random number generation, which is based on the amplitude spontaneous emission, is this a quantum noise? Because there is a quantum effect of this amplitude spontaneous emission, right? And the people claim this is the case as well, right? Because the originator of this is actually either the phase noise of the laser is another thing, right? Because we have spontaneous emission there. Or we have also something like this, let's say some noise that comes from the amplifiers as well, right? And then people claim that this is the source of some quantum. And that is something I quote from them, right? I'm somebody to work on photonic devices. I would be happy also to learn more about it as well, right? But if you consider these as a font for, let's say, quantum random number generation, I think that would be also similar. But I would be happy also to exchange and then ask.
I think we should talk later on. I think and also, or maybe you look at our work on OPOs and random number generation.
Would be
so
great.
This is my strong recommendation here.
Sure. Yeah. Fine.
My question follows. So you in your simulation, you use it just look like Mathematica or something. Why don't you use different time domain simulation? Because if it's really usual for you, it's like FTDD numerical and couple of wavelengths, and normally, usually, it's for your work. It's I did it before, so it's quite easy.
Yes, here we have nonlinear coupling between different signals at different frequencies. I have not seen any FTTD who could do that.
Yeah, I actually did it with nonlinear effect in laser generation. Right now, FTD numerical actually renew, so they have a special code for this, for laser generation, for nonlinear effects, and so we can implement it. It's no problem. Possibly we didn't try just, but a couple of years ago I did it, so it's no problem.
Yeah, it's worth looking into it.
But of course you have to pay for this.
Sure. I mean, what we need to make sure here is that all the different spectrums are being covered as well, right? We need to consider that we have 4 different modes as well, and that is the way that we did separately getting propagated, right? And then losing coupled nonlinear equations, right? But if there is a time domain, I think that would be also something, or time domain simulator that you used or developed, right? That would be also good to look into it, how at least the results are comparing with each other.
I still remember Frank Fitzek saying randomness, we need more randomness to make some codes work. So how is there an improvement in the speed at which you generate randomness using your method?
So I think, I mean, there's also state-of-the-art work. Again, I do not have this here, state-of-the-art study, right? We can go up to, for example, 100 megahertz, right? But let's say, more important thing we would like, that would be more or less the limit for this time. Another study that we looked also at the different signal input is that we would like to make sure if this might have an effect, in order about the statistics of the randomness as well. But what is more important is that we need to look at the bits, right? And that is what we are doing. And then we need to record the bits, send it to Ming, so that there's this NIST test to show how much is the, let's say, quality of the randomness of these bits look like, right? And then as soon as we have that okay from them, then there are ways also to increase this 100 megahertz as well, looking at the different material platforms, looking at some coupled ring resonators to improve it even more as well. But for now, I think the rough, let's say, limit is something like 50, 100 megahertz. This is the limit with this type of structures that I showed.
Sorry, I'm like very, very respectfully, I like to strongly disagree there and really underline it very, very once and for all. A NIST test won't show you that it's random.
I see.
Never, ever. So in principle, I would say a NIST test is only an indication if you have done something completely wrong.
I see.
The Hilbert space, like what we are talking about, is like infinite. And eventually, the NIST test following the logic of Donald Knuth is kind of only probing a certain flaws in a possible random number generator. And this test won't tell you anything. So don't rely on anything like this.
That's great that you mentioned this, right? Because for that, unfortunately, Mark actually left, right, just a few minutes ago. I guess that is what we rely on then, for this test. But that would be good also to maybe discuss also offline about this as well, right? For us, we do a simple test, right? If it's 50% and so on, then I think that would be good to discuss that as well. So how to test the randomness also for that.
So we have banned essentially all these NIST tests out of our papers on randomness generation because we cannot see them as reliable any information. Some referees want them for whatever reason. I don't understand. So we have them maybe in the supplementary, but this is a little ridiculous, I would say.
Nice to know you. Thanks for
So we have more questions. Very good. Now things are starting to roll here.
the last few minutes before lunch.
I'm just going to piggyback on the controversy here. I mean, this is nice work. But I think the key is how do you demonstrate and articulate that you have some really high quality randomness? And just surfing on the idea of what not to do. There's a really interesting paper in Nature Photonics by Ido Cantor from a few years back where they don't use quantum. They use a chaotic signal. They digitize it, do some clever post-processing to amplify noise if you wish. And they claim to have a random number generator that passes the NIST test, but then it violates any result from Shannon. Like it's like way above the Shannon limit. And I think we have to be careful not to fall in that trap. But I don't know, if there is actually something that people would accept as better than the NIST test. In the end, you can only disprove that you have randomness. It's very hard to prove that you have it.
Yeah, I have a question for maybe Ilya, Matthew, everybody here. So Matthew, I agree with you that if you have a perfect understanding of the statistics of a random source, then you know what's the entropy rate. What constitutes a quantum random number generator? What is quantum about a random number generator?
It's good. An experimental word also, kind of.
So I like this is one of my fields which I really enjoy. So what is quantum about a random number generator? And I would say the only quantum thing which there is the proximity to, for example, a Hamiltonian I can write down. And let's say we can argue that, for example, Johnson-Nyquist noise on a normal resistor is already quantum. And then we have already a quantum random number generator if you want. But it's very hard to write down a kind of closed form in a Hamiltonian for Johnson-Nyquist noise. You can do so, but it's going to be pretty complicated. So if you tie it to a kind of the primary source of entropy should be tied to a quantum experiment, so to say. I think this is the only definition, and this goes very close to discussions we had on a workshop we organized on physics and security last year, together with the BSI. Like, this is the German Federal Institute for Information Security. So I would really recommend to. So we should have a debate on this one. And I'm very I think this difference about quantum and non-quantum is kind of an arbitrary one. If you want, we can though discuss about device-independent generators, which are clearly quantum in the sense that you have an information theoretical machine and you ask a question in the form of a Bell test. Then we are very close to some Bell violation or kind of other violations of contextuality, for example. There's also like if you violate one of these kind of typical quantumness measures, then you can prove that you are quantum.
Follow-on question / point. Let's consider, let's say you had a hypothetical ideal laser source and you just watch photon clicks with an ideal detector and you watch that Poisson point process. The origins of that is quantum mechanical. And you can calculate the entropy rate of that. And if you can compress a random number at that rate, then you have quantum randomness. The problem is that we don't know the statistical characterizations of most real-life sources. So in that sense, as you had pointed out, that homodyne detection on vacuum has outcome whose noise are underlie quantum mechanics. But something I have never fully understood is what do we mean by quantum random number? Is the quantumness, is the definition simply that the randomness from which we are extracting the bits have their origins in some sort of a wave function collapse? What qualifies as a randomness that from which, if we were to extract random numbers, that we would call it a quantum?
I think like this distinction is kind of arbitrary, let's say, but I think it's the proximity to a primary source of entropy by Born's rule to have the description in the quantum world as to be a kind of statistical one. There is no other distinction possible because, like, in principle, we can compare the vacuum source, like the vacuum homodyning, very close to this Johnson-Nyquist noise. It's very, very close. I have some very specific answer on like this technicalities behind there, and I think I can put my finger down there. Like, please drop me a line, like, and we can discuss.
So maybe we one more question here.
So the nature of what is random, I have thought about that actually in the context of the homodyne detection and other things. And I think this is actually where, first of all, we don't know the answer. I mean, what we can do, however, using information theory, is provide distances, confidence as to how random this is. And I'm sorry, NIST tests are not that. NIST tests are extraordinarily poorly used methods for claiming randomness, but what one really needs is a guarantee and some kind of a distance metric. Not even a metric. I mean, KL diversion is not a metric, but you can use that. You can never really achieve true randomness. I mean, if you have let's say, the homodyne detector, right, looking at vacuum, you're going to have something that is going to, your output is going to have bandwidth associated with your electronic components reading out. What does finite bandwidth do? It is introducing correlations. So if your adversary has a higher bandwidth receiver, he can or she can go ahead and use those correlations to whatever ends they want. And that's just one fault. Yeah, I'm not even talking about your source being unstable or any other kind of crappiness we find when we do experiments. So, yeah, anyway, this is just distances. It's all about metrics.
Yeah, thank you. I think this is great that I think this sparked this. Just to add things, so we try now to model this, right? We try exactly, that was the motivation for this work. We try to include the phase noise of the laser first, right? Then we would like to see how this vacuum noise would affect this generated random bits as well. And then eventually also if there would be an amplifier, and then eventually also thermal noise. All these things can be done numerically. However, maybe we need also to get the support from all the community here. We have also people from information theory, quantum as well. Maybe a separate session next year, EACN, I don't know, right? Or some discussion during the lunchtime, how really to investigate, because this is not just a discussion here, wherever I present this work, I think maybe a good problem to focus on.
Yeah, I honestly think that NIST has done a great disservice to this community by publishing those randomness tests. And that's probably the only bad thing that NIST has ever done. NIST is a wonderful organization otherwise, but those randomness tests, oh my God.
I think, like the way the tests are described, they're actually very honest about what they are and what they're not. I mean, they don't claim you have a true random number generator if you pass. They really say you don't have one if they don't pass. And but you said something about information theory. That's not going to work either, because the key challenge is not to look at this one bit that you generate. You have to look at the sequence. That's why it's so hard. And computing information theoretic metrics in high dimension is completely impossible. Like, even if you knew the statistics, capturing long-term dependencies is extremely hard. You can't compute anything. And, going back, I was being a bit mischievous, but that paper by Ido Kanter, the reason they passed the NIST test is because they were spreading correlations probably so far apart that they could never be caught by the NIST test that operates on blocks of finite length. But I think it's almost like we need a metaphysical discussion here to agree on what is a true source of randomness. But at the end, we can only disprove. I don't think you can prove. And the hope is that there's a agreed upon model or set of model that people agree are true randomness generators. And then it's all about post-processing to make sure you're dealing with the imperfections. At the end of the day, you can, Sakati was asking, how do you extract? You can always hash. I mean, the more you hash, the closer you're going to get, and you pay a price in terms of rate. You're just mixing bits, but you're reducing the size of your output. So I think NIST did a good job, given the constraints.
I mean, I think maybe I should have not been so critical of NIST. I think it's really the problem of the people who don't read the disclaimers that NIST gives and then basically just use those tests and papers. I guess if NIST had published those tests with blink in red and whatever colors, do not use this test to in proofs of randomness. But I agree with you that the metrics are hard to calculate, but there are shortcuts one can take. Obviously, shortcuts are going to yield more solutions, but ultimately we're going to get into all sorts of computational problems, as you say. So yeah, I agree with you.
So maybe a comment on this very nice discussion. So for randomness generation, maybe what is quantum? A simple answer is that you perform a measurement on a state, and essentially the entropy comes from the collapse of the wave function. So that you measure something that is not an eigenstate of the measurement. So you have entropy by the measurement, right? But then this is not sufficient for security, because the question is your randomness unpredictable for somebody else? And then you have to deal with the question of leakage, the question of can you influence the measurement, and so you might move it to device independent to have this kind of guarantee, so more guarantee. But even in device independent randomness, the best you can hope for is a randomness amplification. You need to have some seed, right? In any model, you don't generate randomness from nothing, right? You need to have some seed, and in some case you can have it also if you verify separation, so you need some assumption, you can have amplification of randomness without characterizing your measurement. But for example, the seed is which measurement you're going to perform. They need to be shared beforehand, right? And so it's not if you want to extract randomness in the end, have guarantees about randomness, even in the device independent case, it's not from out of the